To get started with the groundwater flow modeling tool within GRASS GIS, we will first need to generate the required raster maps. So I showed you in another video how you can generate those raster maps within GRASS GIS. So therefore here I will just simply quickly use or generate the maps I want to have. I will do this by the command line because it's quicker and more reproducible for you if you want to try it at home. But of course, don't forget there is always a graphical user interface and you can use this one. So first of all, what we need to do is we need to set the regions. So as you can see here, I decided to go with an 50 times 100 array, and this in physical units represents 1,000 meters from north to south and 2,000 meters from east to west. The flag minus P3 at the end will simply give me the output for the whole 3D domain because it also defines top and bottom, which is not necessarily here for us. We only do 2D groundwater flow simulation. If you go on the help page of the r.gvflow module, you will get to know what kind of required raster maps there are to run the module. So these are, for example, the initial pressure head, which I will define with this command. So I will simply apply a 30 meter pressure head in the first column and 29 meters just on the other side. I just also use these flag override because if there already is a map with the same name and I don't have this override command, GRASS GIS will throw me an error. And sometimes I'm losing track when I'm playing around a lot if I've already generated this kind of map or not with the same name. So I just use the override flag to always work with the newest version and to avoid this command. The other raster map we are required to generate is the so-called status. The status raster map tells the groundwater flow modeling plugin if cells are active or not. So here all cells within the domain, within the region very much are active. So I have a very simple geometry, just this rectangular 1,000 times 2,000 meters domain. And here I simply say that then the first and the last column, so for the column 1 and the column 100, I want to have the status 2, which means it's a fixed value, so it will take the 30 and the 29 meters pressure head on left and right as Dirichlet boundary conditions. And anything else is 1, which simply means it's active. You can also define other values too, like taking cells out of the computation. Again, more about this would be on the help page of the groundwater flow module. And then we just simply have to define a couple of physical quantities, which is, for example, the hydraulic conductivity. I keep this constant in this simple example here. We need to define top and bottom, the aquifer. So here I used unconfined because we will do this example with an unconfined aquifer. To separate it later, if we want to do a confined aquifer, I will define it differently. But here I'm just saying, okay, it's 100 meters. I principally also need to define a bottom. However, because I just set the bottom to 0 as my base level, I will simply generate a raster map called null, which is 0. But this way null is a bit more general. So if I have, for example, other values, recharge or whatever, I just want to set it to 0, I can always use this raster map null for any kind of case. So I do not get confused if I just call it null. And then we need to define the porosity because we have an unconfined, as I said, example here, which is simply to use the effective porosity of 15% for the storativity. And this is pretty much it. So we have those 6 raster maps which we need. And now we can start the groundwater flow module. So you can do this by going on raster, hydrogeological modeling, and then there is the, oh no, pardon, there's groundwater modeling, and there you have the flow module and the solid transport model. So in principle, you can go here for the groundwater flow tool, and there it says with the stars, it always gives you the explanation, what kind you need on raster maps, status, kind of groundwater flow, if it's confined or unconfined. So there's all these kind of things. You can define recharge, rivers, drainage systems. You can specify solvers, different options, and the command output, as usual for GRASS GIS and help, right? You can do this all using the graphical user interface. I would just do it by command line, but it's the same thing you can use over the graphical user interface. So the command now is quite a lot, but I will walk you through this. So first of all, I'm calling the command r.gvflow. For the top, I will define the top unconfined layer, which we just generated. As a bottom, I will use this null raster map because it just has zeros. For the pressure hat, I define the name of the pressure hat raster map I just defined of a similar name. For status, the similar, and then for the hydraulic conductivity, so the groundwater flow module knows hydraulic conductivity in anisotropic values, so different in X and Y direction. We'll talk about that one later. Here, I'm just assuming everything is isotropic, so I'm not separating between X and Y direction, and simply pass the same hydraulic conductivity metrics or raster map to those two parameters. For the sortivity, I just give the 15% effective porosity, which we just defined, and I tell him for the output, I want him to generate a map called GV result. The type I want to use is unconfined. Now they're coming a bit of more numerical parameters. So far, we have pretty much straightforward. So the groundwater flow module of GRASS GIS is an implicit time discretization, which means it doesn't matter about what kind of time step I give in terms of stability. So what you put in here, which is a bit misleading because it's labeled DT, is actually the amount of time you want to be simulated in seconds. So in this situation, we want to calculate as long as there is a steady state, so there is no temporal change anymore. So I'm just putting pretty much a number here, and we can later see if this has been sufficient or not. I also want the groundwater flow module to calculate the Darcy velocities, so the flow velocities in X and Y direction, and it will generate raster maps of those kind of names. And now there is two parameters I need to specify, which I make to a very, very small number and to a very, very large number. So the error pretty much is because it is an iterative solver, the level of accuracy I want GRASS GIS to calculate until this. So for now, I just recommend going with those numbers for this example. We will later figure a bit out what kind of influence those kind of parameters have on the result. And then I'm just saying again, the flag override, because it might be that if I'm running this command a couple of times, there already has been a raster map with similar names as the output or for the velocities, then it would throw me an error. I don't want that, so I'm just doing the override command. Having this, I'm just hitting enter. And now we're seeing here a lot of different commands. It gives you the iteration accuracy, so the error margin for each solver and so on. It gives you the sum of the water budget, so that should be close to 0 because here we don't have any injection or recharge or anything. And it gives a bit of idea how much the change was between the last and the previous step of the iteration. But it says now that it had generated the raster maps, which we just wanted, so the output of the pressure hat and the velocities. So we should take a look at that. First of all, we're going here in the map display. Already see there is a very strange map. What do we look at? It's the top layers, so this is velocity in Y direction. Why does it look that strange? We can minimize it a bit and put a legend next to it. And we see, well, okay, there is plus and minus actually, and it's very, very small numbers. Why? because we simply have, from the boundary conditions, we apply the flow from left to right. So there should be any flow in y component, at least nothing structured. So what we have here is pretty much just numerical noise. So as this always emphasizes, numerical methods are approximations. So there is nothing like a specific zero, right? There is some oscillation around zero, but you see, I mean, it's 10 to the minus 14 meters per second, which is really, really, really slow. So it is, in numerical sense, zero. But now you already have a feeling for, okay, what kind of numerical noise with this setup, with this spatial resolution, does GRASS GIS has an accuracy based on the numerical method behind it. So next, we can look, which is maybe more intriguing, on the pressure hat. So I will remove this legend and we'll give you a new legend for the pressure hat. And this is exactly what we had as a boundary conditions. We have 30 meters hat on the left, 29 meters hat on the right. And of course, there is almost a linear trend across it. And then we can also look at the velocity, which is interesting to look at. So we'll take here analysis by visualizing all this. And oh, okay, we see there looks like a change from left to right, but pretty much the values are all the same, and they are significantly larger than in the y direction, which is what we would assume because we have a flow from left to right. So we assume we have a pressure gradient from left to right because the pressure gradient is 1 meter over the 2,000 meters distance. And then based on the hydraulic conductivity, we should have some flow velocity, which is okay. But what theoretically we would expect is having a linear pressure drop from left to right means a constant pressure gradient, which means we should have the same velocity from left to right. But why do we see such a gradient? So, for example, there are a couple of methods to analyze our result. We can click here and do a profile across the surface. We do this, we will select the raster map we want to analyze, which is velocity in x direction. And now we can click here to sketch a transect, so which is very much a line. I keep my mouse key fixed, release it. Now it's giving some errors because there are some few points which are not within the domain, which is okay. I know that. I just ignore that. And I see, okay, well, that it can't really plot it because it just says, well, it's all zero, which is, well, I mean, based on the x and y values, it's very, very small. So that one is not really helpful. But we can get us some graphic outputs here, and we see, well, okay, this is, we have 101 numbers, okay. But this is just all giving zero, so this is also not very helpful. But we can analyze this one a bit further. So to do more statistics, we can go here on raster statistics and just give us general informations. We want to do this on not the y velocity, but the x velocity. And now we can see, okay, there is a minimum of 1.244 and a max of 1.28. So now here it's shortened, but it is also 1 e minus 6. So this is, again, not like, quite specific, the value we want to have, but it is oscillating slightly around it, which is just due to the numerical issues we had here. If you remember the command we were giving here, trying to bring that up one again, here with the error and the maximum numbers of iterations, if you play around with those ones, you will see, especially in the x velocity, how the effect changes. However, another thing we would just want to do is say we want to calculate a steady state, and we're not sure if we have just reached it yet or not. So what we in principle can do is we can redo the command just as an input for the pressure hat, removing the raster map we just have generated, but passing the result of the previous simulation and just see if it changes anything. And well, it does not. So we've already reached steady state, but that's a way how we can control it.